Gravity, normal force, and friction are going to be the topics of this lesson. But even more important than that, we're going to encounter our first mechanics problems in this lesson. We're going to learn how to set up free body diagrams and how to set up our equations. This will be foundational for the entire rest of the year. Don't miss this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. All right, so gravity. Now, if you recall, gravity is the weakest of your four fundamental forces. And simply put, it is just an attractive field force between two objects that both have mass. That's the requirement. They have to have mass. And the greater the mass they have, the greater that attractive force. Now, if we take a look at this kind of universally, and then we'll look at the special application of it when you're near the surface of the Earth, which is kind of the gravity that most of us experience. But universally, this is the universal equation for gravity. So your force of gravity, there's a proportionality constant we call the gravitational constant G. But it is equal to m1, m2, the mass of each object in kilograms, all over the distance of separation here. So R here does not necessarily stand for radius, but the distance of separation between the two centers of each of these objects. All right, so we take a look at this equation. There's our gravitational constant here. Sometimes you'll have to memorize that. Some professors do, some don't. It's really up to your professor. So most of you will probably have this provided, just an FYI. If we take a look at this equation, the way this works, so your force is proportional to the mass of the one object, your force is proportional to the mass of the second object, and your force is proportional to 1 over the distance of separation squared. So we can kind of derive these three relationships from this equation. So if you keep everything else the same except you change mass number 1, well, whatever you do to mass number 1, that's going to happen to the force in that case. You double that mass, the force is going to double. You triple that mass, the force is going to triple. The same thing is true for the second mass as well. The force is proportional to that as well. And so again, if you keep everything constant except the second mass, whatever you do to that mass, the same thing happens to the force. Now the distance of separation, so here there's an inverse relationship. As the distance of separation goes up, the force is going to go down, but it's not a 1-to-1. It's not proportional or inversely proportional here. It's inverse proportional to the square. And so in this case, if you double the distance of separation, the force isn't cut in half, it's cut by 1/4. So doubling R here, instead of 1/2, it's 1 over 2 squared, so 1/4 of the force. If you triple the distance of separation, so all of a sudden now, so 3 squared is 9, and so the force is going to be 1/9 as big as it was before. So that's the relationship there. So one, we can just look at these relationships. These come in handy instead of a plug and chug kind of calculation. Sometimes you're just given, a question that involves you deducing the relationship. All right, now we can do some plugging and chugging, and you just have to realize that you've got really 4 variables here. You've got mass 1, mass 2, the distance of separation, and the force, and then G as a constant. And if I want you to solve for something, I've got to provide you 3 of the 4 variables and have you do some plugging and chugging. You got to remember your units. The masses need to be in kilograms, the distance of separation needs to be in meters, and the force will come out in newtons. Now, if you notice here on G, it's 6.67 times 10 to the minus 11. It's Newton meter squared over kilogram squared. And those are the way the units have to work out to make this come out in newtons for a force. So if you keep in mind, if you use SI units, the units will simply just work out. So it's probably worth your time to go through a couple of times and just make sure the units work out. But you're going to see this kind of pattern throughout the course of the year. When you use SI units, things go well. All right. So that's universal gravity. Now, special case on the surface of the Earth. Now, when you're near the surface of the Earth, a couple things get fixed. So you got F equals G. But then one of the masses is the Earth itself, and that's going to be constant. The mass of the Earth isn't really changing. And then you'll have the mass 2. And I could have made the mass of the Earth either m1 or m2. And then the distance of separation here is just going to be the radius of the Earth in this case. And so we get this special case of this equation. Well, G is a constant, the mass of the Earth is a constant, the radius of the Earth is a constant as well. And it turns out when you plug those all in, so if we pull those out, it turns out those are all equal to 9.8 meters per second or 9.8 meters per second squared. And this equation really reduces down to force equals m2g. Well, we rearranged it a little bit and we call the force the object's weight. And since this is the only mass left in the equation, we don't have to call it m2, we're just going to call it m. And then g here is the acceleration due to gravity near the surface of the Earth of 9.8 meters per second squared. So special case of identifying an object's weight, and it's kind of implied that it's near the surface of the Earth unless otherwise specified. Now we could talk about it, on the moon, we could talk about it on Jupiter, we can talk about another number of other cases, but if it's not specified, just assume it's near the surface of the Earth. This is weight as you or I are going to experience it, probably universally throughout our entire lives. Most of us not making it off the surface of the Earth in any significant way. Maybe that'll change with some of the new things coming out, but most likely for most of us, not the case. All right, so now we've got two different situations with gravity. We've got weight, which is probably going to be more common that we deal with, but we've also got this universal form of gravity, and you're going to see this kind of coming up in like planetary contexts and things of that sort. So let's work some problems. That's kind of be the guys here, the pattern that we follow. We're going to introduce a concept, and then we're going to work some problems. So we'll do this with gravity, then we'll do it with normal force, and then we'll do it with friction as well. All right, so right off the handout here, and I'll put it up on the screen, but Jupiter has a mass that is approximately 300 times larger than that of the Earth and a radius that is approximately 10 times larger than that of the Earth. If the acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared, what is it on the surface of Jupiter? So a little bit tricky here. So the exact mass and radius of Jupiter is not given, but relative to what they are on the Earth is provided. So let's kind of see how we approach this question here. So in this case, we look at our setup here, and in fact, it might be easier to kind of look at it right here instead. So what's changing, instead of mass of Earth, we're going to have mass of Jupiter, and instead of radius of the Earth, we're going to have the radius of Jupiter, and we're told how much larger those are than the Earth. Well, in the case of the mass of the Earth, we're told that it's 300 times larger. Well, again, the force and the mass of the planet are proportional. So if you replace the mass of the Earth with a 300 times larger mass of Jupiter, then the force of gravity is going to be 300 times larger as well. Okay, and then we're told the radius of the Earth compared to the radius of Jupiter, Jupiter's 10 times bigger roughly, and so that's going to get 10 squared. And so all of a sudden we can see that the numerator is going to be 300 times bigger, but the denominator is going to be 110 squared times bigger. And so overall, this ratio of GME over RE squared that equals 9.8 meters per second squared on the Earth, it's going to be 300 over 100, 3 times bigger roughly on Jupiter. And that's kind of the rationale we're doing here. Now, if we actually knew the mass of Jupiter and the radius of Jupiter, we would plug those numbers in. And obviously you could Google them and things of the sort. So, but this question is given so that you could reason it out accordingly. All right, so if we take that 9.8 effectively, 9.8, and multiply by 3. So, or multiply by 300 over 100, if you will, we get 29.4. So G of Jupiter is equal to 29.4 meters per second squared. And some people would just write this out as 3G. So 3 times the gravity experienced on the Earth. Now the truth is, these are all rounded numbers I gave you. It's actually not exactly 300, it's like 320, and it's not 10, it's like some change. So, but the big thing is, the real value comes out to 25. But I didn't really care about the real value, so if you're like, hey Chad, I happen to know what the gravity on Jupiter is, and that's wrong. Well, great, you're totally correct. But that wasn't the point of this problem. I really wanted the nice round numbers so we could do the math in our head for the most part. All right, next question. A man has a mass of 81 kilograms. What is his weight on the surface of the Earth? So in this case, because we're dealing with the surface of the Earth, so our equation of interest here is just this guy. We just want his weight. He's, 81 kilograms. So we're just going to go weight equals mg, weight equals 81 kilograms times 9.8 meters per second squared. And we'll do some plugging and chugging here. So 81 times 9.8, and we get 793.8. Now in this case, how many, let's see, that's going to be 2 sig figs. So 793.8 is going to round down to 790, and that's going to be in newtons for 2 sig figs. Okay. Next part of the question says a man has a mass of 81 kilograms. What is his weight on the surface of the moon? And now we have a problem. And if you notice, on this question, the mass of the moon and the radius of the moon are provided. We're no longer at the surface of the Earth. This lovely simple equation no longer applies. Now, if you knew what the gravitational acceleration on the moon was, it turns out it's about 1/6 the value on Earth, we could approximate this, right? But if we didn't know that, we'd have to go the full route and use the universal formula for gravity here. And that's what they're expecting to do here. And I say they, I wrote the question. That's what I'm expecting us to do here because we've provided the mass and radius of the moon. All right, so let's go ahead and do this. And so in this case, we're going to have force equals that gravitational constant, 6.67 times 10 to the negative 11. I'm going to just take it for granted that the units are going to work here. So M1 would be the mass of that moon, and it's 7.346 times 10 to the 22 kilograms. And then his mass is 81 kilograms. You know what? Let me just erase this. We don't need this anymore. And then all over the radius of the moon squared, given as 1736 kilometers. Now you gotta realize it's given in kilometers, we need it in meters. And to go from kilometers to meters, you multiply by 10 to the third. So in this case, instead of 1,736, it's gonna be 1,736 times 10 to the third. So in this case, 1,736,000 meters, and then we need to square that number. And so this force due to gravity on the moon, i.e. his weight on the moon. All right, 6.67 times 10 to the negative 11 times 7.346 times 10 to the 22 times 81 divided by 173, whoop, that's not a 3, 36000 squared. Common mistake, forget to square. And we're going to get 131.69, and once again, we need to round this to 2 sig fig, so 130 newtons. And again, we said that the gravity on the moon is roughly 1/6 that of the Earth, so the weight should be roughly 1/6. And 130 is about 1/6 of 790 newtons, so totally worked. All right, so now we're going to move on to talking about the normal force and friction. So a couple, just a reminder that force is a vector. It has both magnitude and direction. And that's going to be true of all the forces. Gravity, we saw, pointed towards the center of the Earth, which we usually experience on the surface of the Earth is pointing down. But it has both magnitude and direction. Same thing's going to be true for every force we look at. So normal force, if you're trying to figure out the direction of a normal force, the name is the clue. Now, when we say the word normal force, it's not the normal use of the word, no pun intended. So if you were to say that, Chad's a normal guy or Chad's not a normal guy, that's not the use we're going for here with the word normal. Normal here in a physics or mathematical sense means the perpendicular. And so a normal force is always a perpendicular force. That's where the name actually comes from. And it's a contact force. When two objects are in contact, and oftentimes it's one object with some sort of flat surface, so it is the force perpendicular to the surface at the point of contact. So right now I'm standing on the floor, and gravity is trying to pull me to the center of the Earth. But right now the floor is pushing back, and the perpendicular component of that force, and in this case I would argue that it's all perpendicular, so that is the normal force. And the most common example of normal force is just this. It's the contact force between an object and the ground, and usually they're perfectly balanced. Whatever the force of gravity is, the normal force pushes back with an equal but opposite force, according to Newton's third law. And you'll find out pretty commonly the normal force equals the weight of an object. Now, it's not always true though. So let's say, for instance, we'll get this book here. So nice flat surface. And I'm going to put this lovely eraser right on top of it. And right now there's a normal force. The book is exerting a normal force on the eraser, pushing back on it. And it should be equal to the eraser's weight. No big deal. And so that's, again, what's commonly true. Now, we got a couple different options, though. What if I take, and I'm like, I feel bad for this book. I'm just going to help it bear the load here. And I'm going to take a little bit of the weight off. And I don't lift up the eraser completely. But now, because I'm pulling up a portion of its weight, holding it up, then the book doesn't have to do as much. And now all of a sudden, the normal force from the book is actually less than the object's weight. But we have the opposite situation as well. I can be pushing down on the object. And so in addition to the object's weight, we now have a downward force being applied to it, and the book is still balancing both of those. And so now the book is not only having to balance out the object's weight, but also the downward force that I'm applying. And so the total normal force is actually greater than the eraser's weight. Cool? So that's normal force, and again, perpendicular contact force. All right, we had to bring up normal force before we could talk about friction here, because it turns out that the friction between two objects is going to be completely dependent upon the normal force and actually be proportional to that normal force. So friction is also a contact force. And it turns out that friction always opposes motion. So if we take a look back at this eraser in this book again, so if I want to move the eraser to it's my left, it's your right. If I want to move it to the right, friction is going to oppose that and push back to the left. On the other hand, if I wanted to move the eraser to the left, then friction is going to push back and oppose it that direction as well. Friction always opposes the motion. It's an example of what we call a non-conservative force that we will get more to in the next chapter, it turns out. So friction always opposes motion, but it's also a contact force. If these weren't in contact, then there would be no frictional force. And it turns out it also depends on the normal force. So if we go back, and again, if I just try to push this like this, but if I'm pushing down on this and now try to slide it, it's harder to slide back and forth because there's more normal force in that situation where I'm pushing down again. And so the greater the normal force, the greater the friction as well. So it turns out if we take a look, there's two types of friction. There's static friction, and so we're going to have force of friction static, and it's going to equal some sort of frictional coefficient, static frictional coefficient, times the normal force. Now, a couple different ways textbooks abbreviate normal force. I like using F sub n, so it's just really convenient. Some just use a capital N, not my personal favorite, because that's what a Newton is and stuff like this, but someone will be like, well, I put an arrow over it, Chet. So, and that's great and all, but not my favorite. I'm going to use F sub n for normal force. What's the word I'm looking for? I'm going to use F sub n for normal force all the time throughout the entire year, just an FYI. All right, so it turns out there's two equations for normal force because another one here, force of friction kinetic, equals mu k, again, times the normal force. And so it turns out there's static friction and there's kinetic friction. Okay, well, what's the difference? Well, think about this. If, let's say you got a box lying on the floor and it's full, it's got a lot of stuff in it, it's a pretty heavy box, and you go to slide it along, say, a tile floor or a laminate floor or something like that. And it's heavy, and so it's hard to move. But once it breaks free, all of a sudden it jumps. And then to keep sliding it, though, takes less force than it took just to get it going. And so it turns out when when two objects are in contact for a while, they form some spot welds, some molecular spot welds together and stuff like that. And those have to get broken to get it moving. But once it's moving, you don't have to break those again. And so it doesn't take as much force to keep it moving. And so it turns out there's two different coefficients of friction. There's the static coefficient of friction and the kinetic one. And the static one is typically higher than the kinetic one, reflecting that it takes, you're going to get greater friction to get that object moving than to keep it moving in the kinetic case. Now, one other thing to note. So it turns out that for the force of static friction, so we have some special cases like on an incline we'll see. And if I start putting this on an incline right now, so friction is keeping this thing from sliding. Friction's keeping this thing, but eventually, if I get the incline big enough, force of friction, in this case static friction, is not going to be enough to keep it from sliding. And so it turns out that the force of static friction is not always going to actually equal this much. So, but this is ultimately going to be the maximum amount that it could possibly be. This is the max that it could be. So, and again, if I go back to my incline example, as long as I give this and don't incline it too far, so have I reached the maximum yet? I don't know. So, but I know it's not more than the maximum. So have I reached the maximum yet? I don't know, but it's not more than the maximum. And all of a sudden, oh, there it goes. And so right before, right when I've given it that incline, right before it starts to move, that eventually reaches the maximum. But everywhere up until that point, when the angle was smaller, we hadn't reached the maximum yet. And so the force of static friction doesn't always actually equal this formula. That's the maximum it could ever equal. And the incline is a great place where, is it equal to the maximum? We don't know. We just know that it's never going to equal more than this amount right here. All right, so to figure out the force of friction, you first got to figure out the normal force, and we will routinely do that. So a couple things you should know. Units of force are newtons. So notice normal force is newtons, force of friction is newtons, which means that your coefficient of friction in either case has no units. And it's customary, you'll typically see these having a value less than 1. So, but they're unitless, that's important to know. So let's work some problems here. All right, so we're gonna put a 50 kilogram woman on a Newton scale in a stationary elevator. What should the scale read? So let's take a look at our elevator here. We've got a scale on that elevator, and we got a woman who's a stick figure woman standing on that scale. And it's a Newton scale, so it actually reads weight in newtons. So, and this is on a stationary elevator. What should the scale read? Well, this lady's weight, if we do weight equals mg, 50.0 kilograms times 9.8 meters per second squared. So, and in this case, notice 100 times 9.8 would be 980. So 50 times 9.8 would be 490 newtons. It's got 2 sig figs, and it should have 2 sig figs. The 50.0 had 3 sig figs, and the 9.8 has 2. Notice I only wrote 50, but on the sheet it does say 50.0. All right, so she weighs 490 newtons normal. That's what a scale would read. So, but if you notice, her weight is pointing down on that scale. So we're going to draw what's called a free body diagram now. And we can draw a free body diagram for any object, and it just is a diagram that diagrams out all the forces acting on a particular object. Okay, so in this lady's case, what forces are acting on her? Well, her own weight. And so pointing in the downward direction, we have her weight. So in this case, though, what's pointing up on her is there is a normal force coming off the scale. So she's standing on the scale, she's in contact with that scale, and it's pushing right back. Now, if she's on a stationary elevator, I have a question for you, is which one of these forces is stronger? I like to think which one wins. Well, neither one. It's kind of like the floor right now. My weight's pushing down on the floor, and the floor is pushing, or weight pushing down on me anyways, and the floor is pushing back, but I'm not accelerating up or down. I have no net acceleration. My motion in the vertical direction is not changing whatsoever, so there must be no net force. So that's the same for this lady. There's no net force in the vertical direction, which means these forces must be equal in magnitude, though opposite in direction. And so if we take a look at Newton's first law, said that for an object whose motion is not changing, which either means it's not moving or it has constant velocity, so in the vertical direction here, that sum of the forces is 0. Now this is a one-dimensional problem because we're only considering motion in the vertical direction, but it's customary so that we're going to start seeing two-dimensional problems, and you'll treat the x dimension and the y dimension separately, just like we did in the kinematic section. But instead you'll be doing it with the forces. And so the sum of your forces, if there's no acceleration, if there's no change in the motion, either because the object we're looking at is either not moving in that dimension or moving at constant velocity in that dimension, but either way there's no acceleration, then the sum of the forces equals 0, just like we saw in Newton's first law. So if there's no change in the motion in that dimension, sum of the forces equals 0. Sometimes we call that a state of equilibrium. All right, so sum of the forces equals 0, and in this case, what are those forces? Well, the normal force and the weight. So it's customary to make forces that point up positive and forces that point down negative, forces that point right positive and left negative in the x direction. So, but the truth is, I guess you could define it however you want to, but we should define it, which is, how it's done customarily, because that's how likely your textbook and your professors are going to do it as well. So we're going to make up positive, down negative. And so if we set up this equation now, sum of the forces equals 0. Well, what are those forces? Well, we have the normal force minus the weight equal 0. There's only two forces, normal force and weight, and they add up to a total of 0. Now here's the deal. When we do equations like this, you're never going to plug in negative 9.8 for gravity. You're always going to use the absolute value in the sum of the forces equation. And you're going to account for the direction yourself based on the sign in front of the force. So just keep that in mind. All right, so normal force minus mg equals 0. If we rearrange this, we're going to get that the normal force is equal to mg, just like it is for me right now staying on the ground. The normal force from the ground applying to me is perfectly balancing my weight, just like it is for this lady. And so in this case, we figured out her weight was 490 newtons, and so the normal force is 490 newtons. And here's the deal. That's ultimately what a scale reads. A scale doesn't actually read your weight. It reads normal force, pushing back. But again, most of the time that's equal to your weight. When is it not? Well, we've got some elevator examples when it's not. Let's take a look. All right. 50-kilogram woman stands on a Newton scale in an elevator moving downward, key, with a constant velocity of 1.0 meters per second. What does the scale read now? And this is tricky because the elevator's moving down, and you might be tempted to think, and I highly recommend you think about your last time you're on an elevator, and if you haven't been on one recently, go get on one, jump around, things of this sort, have some fun on that elevator. Make sure it's fairly new and in good working order, but go have some fun on that elevator. And what you're going to find is at the very beginning of the journey on your elevator, it's going to accelerate, but then it's going to achieve some sort of constant velocity, maximum velocity until it reaches the floor. And then it's going to come to a stop at whatever floor you're stopping at. Now, if you think about this, depending on if you're starting the journey going up or starting the journey going down, you're going to experience something a little different. Now, when you're at the top and you start the journey going down, it feels like the floor just drops out from you, and all of a sudden you feel a little, light in your stomach and things of this sort, because you actually are feeling a little bit light. If you were standing on a scale at that exact instant, when the elevator accelerates downward, it would no longer read your weight anymore. It would read something lighter than your actual weight. But instead, let's say you're going up to a higher floor. So when that elevator first starts and it accelerates upward, so now all of a sudden, you're going to feel heavy, and you're going to feel it in your legs, and you're going to feel, it in your feet and things of the sort. And if you look down at the scale at that instant where the elevator accelerates upward, indeed, you don't just feel heavier. So according to the scale, you are heavier. Well, again, your actual weight hasn't changed. Your actual mass hasn't changed. So what you're going to find, though, is that there's a different normal force, and that's what the scale is reading. It's reading normal force. Even though your actual weight hasn't changed, the scale's reading normal force, not weight. And as long as the scale balances its normal force is balancing your weight exactly, it'll read your weight. But if it's not, it's going to read normal force. All right. So let's see how this works. So in this case, again, this 50.0 kilogram woman stands on a Newton scale in an elevator, moving downward with a constant velocity of 1 meter per second. So she's already reached the cruising speed of the elevator. It's moving at constant velocity. Well, as long as it's moving at constant velocity, nothing has changed here. If it's at constant velocity, then Newton's first law still applies, and the sum of the forces is still zero, and the math works out exactly the same, and her Newton weight is still 490 newtons. But the last problem here, a 50-kilogram woman stands on a Newton scale in an elevator that is accelerating 2.0 meters per second squared downward. What does the scale read? All right. So now things are going to be a little bit different. Now, personally, I look at this and I say, okay, gravity is normally 9.8 meters per second squared, but if she's accelerating 2.0 meters per second squared downward, well, when the elevator accelerates downward, you feel like the floor just dropped out from under you. You feel lighter. And in this case, I've gotten used to this, and I just subtract the 2 meters per second squared her acceleration in the elevator's acceleration, right off gravity. And I just use, instead of 9.8, I'm going to use 7.8 and find out what her weight is. But we want to see why that works, not that it works, but why it works. And we really need to focus on proper setup of the problems here. So new free body diagram. She's still on a scale. She's still in an elevator. But let's take a look at these forces now. Well, she still has her weight pointing down, and she still has a normal force from the scale pointing up. That hasn't changed, so it's the exact same free body diagram. The difference is this. There's an acceleration. Her motion is changing. Newton's first law doesn't apply anymore. It is Newton's second law that's going to apply instead. Personally, I like to think that Newton's second law always applies. I don't even actually think about Newton's first law. I just always write this equation. This is where I start. Sum of the forces equals ma. If a happens to be 0, well then sum of the forces equals m times 0, which is still 0. And it's by default turns into Newton's first law. But either way, this is typically where you're going to start. And so here we'd look at the sum of the forces, and again in the vertical direction, it's normal force and weight. Normal force minus mg equals ma. And in this case, we'll rearrange this a little bit. So normal force equals ma plus mg. And the reason I'm solving for the normal force is that's what the scale reads. That's what the scale reads. Now we got to be a little bit careful here because I've made the classic error. And if you look at what's going to happen here, we're going to get, okay, normal force equals mass, and then A plus G. If I factor out that mass, and you're like, oh, Chad, it's actually 2 plus 9.8, and that's 11.8. You're right, but I made the classic mistake here. So if we take a look at what's wrong with this, well, notice we defined up as positive, down as negative. And we did that for Fn and mg. We should have also done it for MA. And the question is, was her overall force up or down? Because was her overall acceleration up or down? Well, in this case, we were told that she's accelerating downward. And as a result, we should have put a big fat negative sign over here for MA as well. And so signs are super important. If the overall force and acceleration are downward, then you better put a negative MA in there as well. And so if we go back and redo this just a little bit, it's negative MA plus mg. And so in this case, we could look at this as G minus A. Let's invert it a little bit. And I can see why that worked, why I took the 9.8 and I just subtracted off the 2 and used 7.8. That's why it works. Now, again, that's my just way of quickly remembering how to get to the answer without thinking about it too hard. But as long as we do the proper free body diagram, we had to remember to make MA negative on the right-hand side. That's ultimately where it comes from. So let's work this out. So the normal force, which again is what the scale reads, is going to equal 50 kilograms times 9.8 meters per second squared minus 2.0 meters per second squared. And then again, it's her mass times that 7.8. And we're going to get 390 newtons. So notice her true weight, again, is still 490 newtons. That hasn't changed. But the scale's not reading that anymore. The scale's only reading 390 newtons because, again, the scale doesn't, in principle, read weight. It reads normal force. And again, as long as your normal force equals your weight, life is good. But in a case where you have an elevator either accelerating downward or accelerating upward, that's not true. Now, if we had the same elevator and it was accelerating upward, just starting its journey to the top, if you will, be one example, with an acceleration of 2 meters per second squared, well, then we would have found that it would have worked out the exact opposite way. Instead of G minus A, instead of having negative MA on the right, we would have had positive MA, and it really would have been G plus A on the right. And instead of 9.8 minus 2.0, it would have been 9.8 plus 2.0. We would have found out the normal force read heavier than her actual weight instead of lighter. So now we're going to take a look at some friction problems. So and go from there. So the first one, it's technically not going to be a friction problem as we'll see, but it's setting it up for the second problem. A 10.0 kilogram object is being pulled horizontally along a frictionless surface. Okay, so we got a 10 kilogram object being pulled along a frictionless surface horizontally with a force of 50.0 newtons. What is the magnitude of the acceleration of the object? Okay. So for these kind of problems now, classical mechanics problems here, we have to set up what's called a free body diagram. And a free body diagram maps out all the forces acting on an object. In this case, this 10 kilogram mass. What are all the forces acting on it? Well, we know there's a 50 Newton force operating horizontally. Now I drew that out to the right. I could have drawn it off to the left. It just said horizontally. So but that's why the question's only asking for the magnitude of the acceleration, because it didn't know what to give for a direction, because it never actually claimed a direction and stuff. So but that's one of the forces. What other forces are actually acting on this object? Well, it still weighs something. It has a mass, so it has a weight. And weight equals mg, and always points down in this case, towards the center of the Earth. So, and then there's a contact force, a normal force, operating upward as well. And that's all the forces. Now here's the deal. In the y direction, these forces are balanced. There is no motion in the y direction. This thing's not jumping up or anything like that. There's no motion in the y direction and definitely no acceleration in the y direction, no change in its motion in the y direction either. And so the sum of the forces in the y direction are going to add up to 0. So in the y direction, the sum of the forces are adding up to 0. Now in the x direction, we have a little bit different story. The forces aren't balanced. There's a force pointing to the right, but it's a frictionless surface, so there's no friction opposing the motion, and there's no other force in the x direction, that horizontal direction, so that some of the forces are going to add up to ma, specifically in the x direction. So we're splitting up the problem into two dimensions. Just like we did for kinematics, we're doing it here, and you can treat the x and the y separately. So when you set up your free body diagram, so you're going to take all the forces that are operating in the vertical dimension, and you're either going to set them equal to 0 or set them equal to ma, the y component of this acceleration. How do you know which? The question is the motion changing in the y dimension at all? Well, no, this thing's not moving up or moving down or changing or accelerating in any way, shape, or form. So it's just going to add to 0. But in the x direction, that's not true. We see there is going to be a net force in the x direction. If there's a net force, then there's also a net acceleration. And so that some of the forces are going to add up to ma instead. But these are your options. Either this is said to be an equilibrium, and the sum of the forces will equal 0 in that dimension, or it's not an equilibrium, and the sum of the forces will equal ma in that dimension. So, but this is kind of your classic setup. And so in this case, we want to solve for the acceleration, which is in the x direction. So that's where we should start. So and in this case, what are the sum of the forces? Well, there's only one force. There's 50 newtons. Object's mass is 10 kilograms. And I realize this is 50.0 newtons and 10.0 kilograms on the question. So, and right now we have enough information to solve for the question. It wanted the acceleration, which is all in the x direction. We didn't have to actually set up this equation at all. Now we could have. So it's customary to have forces that point up as positive and down as negative, just like it is to have forces that would point to the right as positive and left as negative. And so in doing so, we could have set up normal force positive minus mg equals 0. But we didn't need to. We didn't need to set up this equation in order to solve what they're asking for. And so why bother? Just a waste of time for this question, but we will need it for the next one, as we'll see. So if we go ahead and solve for that acceleration, so 50 newtons over 10 kilograms is 5.0 meters per second squared, and I gave it 2 sig figs. I guess actually I perhaps should have given it 3 sig figs. Yeah, that's actually going to need 3 sig figs. So let's get 5.00 based on the numbers that are actually provided in the question. So 5.00 meters per second squared. Okay, there's the magnitude of our acceleration. So now what happens if we add friction into the mix? All right, so next question, same numbers with one big exception. A 10.0 kilogram object is being pulled horizontally with a force of 50.0 newtons, resulting in a net acceleration, so far so good, but resulting in a net acceleration of only 4.0 meters per second squared. And then the question is, what is the coefficient of kinetic friction between the object and the surface? And so here's the problem. We're not told it's frictionless now. Friction always opposes the motion. We know there's motion in the positive x direction here. There must be a countering force back for kinetic friction. Always opposes the motion. That's why we're not coming out with an acceleration in that same direction of 5.0 meters per second squared. It's only 4, because there must be some counter force, so kind of negating some of that 50 newtons, if you will, so that we're not ending up with an overall net force quite as high as in the last example. Okay, so how's this going to change things? Well, it's going to change things in the x direction for our sum of the forces equation. We still have a sum of the forces that is going to equal ma. So that hasn't changed. But now instead of just a 50 Newton force, we have a 50 Newton force in the positive x direction and the force of kinetic friction in the negative x direction. And so we're going to say 50 newtons minus the force of kinetic friction equals max. Okay, this is the way this works. Now we still know the net force is still in the positive x direction, so that won't seem super important now, but it turns out it does matter that we made max here positive. So what we're doing here, and you have to realize this, is that we're going to take every single force, including the sum force, the net force, and we're going to decide if they're positive or negative. The 50 newtons, the way I drew it, it pointed to the right, I made that positive. The force of friction pointed to the left, and so I put a negative sign in front of it. Same thing over here. The net force also points to the right, and so I left it positive. But sometimes we'll end up putting a negative sign in front, as you'll see. So if you look at that, some of the forces in the y direction, so normal force pointed up, I made that positive. but mg pointed down. I made it negative. Now here's the deal. You're never going to plug in negative 9.8 for g in such instances. You're always just going to plug in plain old 9.8. The way you're going to account for the sign is in front of the entire force term. If it points up in the y direction, you'll make it positive. If it points down, as the weight does in this case, you'll put the negative there. But if you put the negative there and then put a negative 9.8 there, the whole term is going to come out positive. So no more negative 9.8s when dealing with mechanics problems. You're going to account for the signs in front of the force terms at large. Okay. So going back to this problem here, so we want to solve for the coefficient of kinetic friction, which is going to be part of that friction term, but we know this acceleration in the x direction is 4 meters per second squared, and we can plug some stuff in here. So 50 newtons, force of kinetic friction is mu kinetic times the normal force. And that's going to equal our mass of 10 kilograms times the acceleration of 4.0 meters per second squared. And then the normal force. Well, we're going to have to go back here. And to get our normal force, now we do have to deal with what's going on in the y direction and solve for it there. And again, people often get to the point where they're just like, oh, the normal force equals the weight. And most of the time that's true, but it's not always true. And they just kind of take it for granted that it's true. Well, why was it true? Well, we had the sum of the forces equaling 0 in the y direction. And so normal force minus the weight equals 0. So the normal force must equal the weight in this example, which is 10 kilograms times 9.8 meters per second squared, which is 98 newtons. Okay, so going back to our problem here, we now have 50 newtons minus that coefficient of kinetic friction times our normal force, which we just figured out was 98 newtons, is going to equal 4 times 10, 40 newtons. And there we go. And so we'll subtract the 50 to the other side. We're going to end up with negative mu times 98 newtons equals negative 10 newtons. And then we'll divide through by the negative 98. And so if we do negative 10 divided by negative 98, we're going to get 0.102 as mu k here. And in this case, I think we need 2 sig figs based on the numbers provided, so it's just going to be 0.10. And my question for you is, what are the units on that again? And again, coefficients of friction are unitless. Again, looking back at the equation, normal force is newtons, frictional force is newtons, therefore the coefficient of friction must have no units. It's unitless. And so the answer to this question is just simply mu k equals 0.10 for our coefficient of kinetic friction. All right, we got one more problem. We're going to make this a little bit worse. And I think we need a clean board for this. All right, in this question, we're told that a 10 kilogram object on a horizontal surface, and the coefficient of kinetic friction, mu k, is given as 0.20, is being pulled with a force of 50.0 newtons, and here's the horrible part, at an angle of 30 degrees below the horizontal. What is the magnitude of the acceleration of the object? And this kind of sucks. So if we look, it's not being pulled horizontal anymore. So this time around, we're told it's being pulled at an angle 30 degrees below the horizontal. It's still 50 newtons, but 30 degrees below the horizontal. And that sucks. This is the first time we've dealt with a force that wasn't perfectly the x direction or perfectly in the y direction. And what we're going to have to do is break it up into components, because that force now has an x component and a y component. And the x component is going to equal 50 newtons times cosine of 30 degrees. And the y component is going to equal 50 newtons times the sine of 30 degrees. So that's the rub here. Now if we finish up the rest of this diagram, we're definitely still going to have a force of kinetic friction. We're still got the object's weight pointing down and the normal force pointing up. And so we're still going to have some sum of the force equations. So we're going to have the sum of the forces in the y direction still adding up to 0. This thing still has no change in motion in the vertical direction whatsoever. It's still sliding along this way, but notice it's not moving lower, not moving higher, not accelerating lower, not accelerating higher. And then we're going to have some of the forces in the x direction equaling max. So we're still told to calculate the acceleration, which is all in the x direction. So here's our free body diagram. Here's some of the forces equations. And we have to account that this lovely force of 50 newtons, part of it is in the x direction, it'll be part of this equation, but one component of it's in the y direction, it'll be part of this equation instead. That's the rub. And so if we take a look here, so for the y, normal force still points up, I'll make it positive. mg still points down, I'll make it negative. But this component of the pulling force is directed downward, and so I'll subtract it as well, and it's 50 sine 30. And so normal force pointed up, these both pointed down, made normal force positive, made both of them negative, and it adds up to 0. So that's the y. In the x direction, we've got 50 cosine 30, pointing to the right, so I'll make that positive. And we've got the force of kinetic friction pointing to the left, I'll make that negative. And that's equal to max. All right, so one thing to note, if your net force, the ma, points in the positive direction, then you leave it alone. If it points in the negative direction, you got to put a negative sign in front of it as well. So it's not just enough to determine the signs of what's on the left-hand side, you've got to do it for the net force as well. Well, in this case, that net force, friction never wins. Friction doesn't overcome your pulling force. It's going to oppose it, but it never wins, right? Friction can't pull harder. If it overcomes the motion, everything stops. And once it stops, well, then friction stops too. So friction always opposes motion. So in this case, the net force and net acceleration are going to be to the right, which we defined as positive, so it's going to be positive here as well. There's no negative side needed in front of there as well. All right, but these are fundamentally our equations, so we want to still solve for the magnitude of the acceleration of the object. That's still what we need to solve for, but to do that, we need some help from the other side. So here, let's put some numbers on this. 50 cosine 30. That's going to give us 43.3 newtons. And then minus force of friction, kinetic, and again that's mu k, which in this case is 0.20, times the normal force, which we don't know yet, equals ma, 10 kilograms, and again that's acceleration we want. And so in order to solve for that acceleration, we have to know the normal force. To solve for the normal force, well, that's what we're going to get from the y direction here. And so in this case, normal force is going to equal mg plus 50 sine 30. Oh, moving those to the other side. And so in this case, mg is 10 kilograms times 9.8 meters per second squared. And then 50 newtons, sine of 30 is just a half. So 50 times sine of 30 is just going to be 25 newtons. Well, 9.8 times 10 is 98 newtons. 98 plus 25 is 123 newtons. There's our normal force, which we're going to again plug in right back there. And now we know everything we need to know to solve for that acceleration. So 43.3 newtons minus 0.20 times 123 newtons equals 10 kilograms times our acceleration in the x direction. All right, so 43.3, let's see, what's 0.2 times 123? So 0.2 times 123 with our frictional force actually comes out to 24.6 newtons. So 43.3 newtons minus that 24.6 newtons is going to get us 18.7 newtons equals, again, 10 kilograms times our acceleration. We'll divide by 10, which is going to turn out to 1.87. And in this case, we need to round to looking like 2 sig figs based on the coefficient of kinetic friction supplied. And so your acceleration, which is all in the x direction, is going to be 1.9 meters per second squared. Cool. So a lot of students really struggle with this one. They remember that the pulling force is only an x component of 50 newtons cosine 30. They're cool with that. So it's not all 50 newtons, it's only like 43.3 of the newtons. Okay, what they forget is that because part of the force is directed down, that's going to actually increase the normal force. It's not 98 newtons anymore, it's 98 plus an additional 25, because now in this case, the normal force not just balancing out the weight, but balancing out part of the force that is pulling down. And so you have to add those two together to get that normal force effectively. So that's what a lot of students forget. And so they'll do this setup good, but forget they have to account for the fact that one of the forces points down here. So get a good system for setting up free body diagrams. Personally, I like setting things up so that all my stuff in the X direction is in one color, all my stuff in the Y direction is in another color. So do what works for you. But when you have a force that's directed somewhere in between the X and Y axis, it's gonna have components, and you're gonna have to split it up into components just like we've done with our vector math up until now. Now, drawing these free body diagrams and setting up the sum of the forces equations, and sometimes in one dimension and sometimes in two, and figuring out, do the sum of the forces add up to 0, or do the sum of the forces add up to MA, making sure you get your signs correct, super foundational, again, to the entire year. So, and hopefully we've given you quite a few examples in this lesson, but there'll be several more throughout the remaining lessons in this chapter. Now, if you found this lesson helpful, consider giving it a like. Happy studying.